Alright, so we're going to have a look at another question from the topic of linearity. So we have let capital X equal R3 and let capital Y equal the set alpha 1, alpha 2, alpha 3 such that alpha 1 is the vector 1, 1, 0, alpha 2 is the vector 1, 0, 1, alpha 3 is the vector 0, 1, 1. We are asked, does capital Y span capital X? Okay, so what we're going to do here is we're going to introduce three constants. So we're going to set up some constants. I'm going to call them lambda 1, lambda 2, and lambda 3. We are going to introduce a new vector, which we might call beta 1, beta 2, beta 3. And this vector is going to be contained in Y. And it is going to be a linear combination of these constants, these scalar values, when multiplied by the three vectors alpha 1, alpha 2, alpha 3. So this is equal to lambda 1 times 1, 1, 0 plus lambda 2 times 1, 0, 1 plus lambda 3 times 0, 1, 1. Now we can expand this out, turn this into one big vector. So our x component will be lambda 1 plus lambda 2. Our y component will be lambda 1 plus lambda 3. Our z component will be lambda 2 plus lambda 3. And this is equal to the vector beta 1, beta 2, beta 3. So exactly as we've done previously, we are going to turn this into a matrix. So we are going to say that this reduces to lambda 1, lambda 2, so that's 1, 1, there's no lambda 3, 0. This is equal to beta 1. And then we have lambda 1, lambda 3, so that's 1, 0, 1. And this ends up being equal to beta 2. And then we have lambda 2, lambda 3. So this is 0, 1, 1, beta 3. And then we need to try and row reduce this matrix. If we get a row of zeros, then we essentially have what is equivalent to a free variable, and that will mean that there is some restriction on the span of y. So the span of y will not be R3, it will be R3 with some certain condition. If we can row reduce this and get a diagonal of 1s, then they're linearly independent, then we don't have a problem. So what we'll do is we will say row 2 becomes row 2 minus row 1. We'll say, well, we'll leave row 3 for the moment. So we have our new diagram is 1, our new matrix is 1, 1, 0, beta 1. We are subtracting row 1 from row 2. So 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, beta 2 minus beta 1 is beta 2 minus beta 1. And then the end row is 0, 1, 1, beta 3. Now we are going to modify row 3. We're going to say the new row 3 is the old row 3 plus row 2. So we get 1, 1, 0, beta 1 up the top, and then we have 0, minus 1, 1, beta 2 minus beta 1, and then the bottom row we are going to add row 2 to it. So 0 plus 0 is 0, 1 plus minus 1 is 0, 1 plus 1 is 2, beta 3 plus beta 2 minus beta 1 is, I need to expand this bracket a little bit, this is going to be beta 3 plus beta 2 minus beta 1. So now we can divide row 3 by 2. So row 3 becomes row 3 divided by 2. This gives us the new matrix 1, 1, 0, beta 1. We get 0, minus 1, 1, beta 2 minus beta 1, and then we get 0, 0, 1, beta 3 plus beta 2 minus beta 1. So now this is all divided by 2. Now we have to take row 2 and we have to subtract row 3 from it. So row 2 minus row 3. So we're going to get 1, 1, 0, beta 1. It's going to become a little messy. We've got to be careful with this term when we move it around. This row will become 0, minus 1. 1 minus 1 is 0. Beta 2 minus beta 1 minus this. Well, we've got a beta 2 and we're subtracting beta 2 on 2. So we've got a beta 2, we're subtracting a beta 2 half. So that's beta 2 on 2. We've got a minus beta 1. We're subtracting a minus beta 1 half. So that's adding beta half. So that's minus beta 1 on 2. And then we've got minus beta 3 on 2. Minus beta 3 on 2. And then our end row is still 0, 0, 1. Beta 3 plus beta 2 minus beta 1 on 2. And now we are going to multiply the middle row by minus 1. So this becomes positive. So these are around now all positive. These both become positive. This becomes negative. And now all we have to do is take row 1 and it becomes row 1 minus row 2. So we're going to get 0, 0, 1 down the bottom, which is beta 3 plus beta 2 minus beta 1 over 2. We've got 0, 1, 0 in the middle, which is beta 1. Well, these are all on 2, so this will be beta 1 minus beta 2 plus beta 3 on 2. And then the top row, we will be subtracting the middle row from the top row. So we have a beta 1, then we're going to be minusing beta 1 on 2. So that will be beta 1 on 2 minus beta 2 on 2. So beta 1 on 2 plus, so this will be beta 1 plus beta 2 and then minus beta 3 on 2 minus beta 3 on 2. This is 1, 0, 0. So this actually reduced completely. We've got a nice row of diagonal ones here. And therefore, the three vectors, alpha 1, alpha 2, and alpha 3, are linearly independent. Now this is an important result because if we get up to this step and we get an actual proper reduction, this implies that the span of y is equal to R3. Because they're linearly independent, they're three-dimensional, there are three of them, they're linearly independent, they get everywhere in R3. If the span of y, we should say that this is capital Y, span of capital Y is equal to R3, given that the span of capital Y is R3, this implies that the span of y, capital Y, is equal to the span of x, span of capital X. So does y span x? Yes. Yes, it does. And this is the answer that we're after in this case.